Okay, in this lesson we're going to do our first hypothesis test involving mean. We have the sleep times for 12 individually selected adult subjects were collected. The sample mean was 6.833 hours of sleep, and the standard deviation was 1.992408984. A lot of digits in here because we have a really small sample size, so we're trying to be as accurate as possible. A common recommendation is that adults should sleep between 7 and 9 hours each night. And when we look at this, we're going, whoa, look at that. Our mean is, I would have expected it to be between 7 and 9. So our mean is not even between our two limits that we're discussing here. So that kind of prompts our question. We are going to use a 5% significance level to test the claim that the mean amount of sleep for adults is less than 7 hours, and then interpret those results. So we need to go ahead and get started. Again, our null hypothesis is always going to have the equality sign. So we have mu is equal to 7 for our null hypothesis. Our alternative hypothesis is mu is less than 7, and we get that less than 7 from this phrase right here, the very last line. We're testing to see the mean amount of sleep for adults is less than 7 hours. So that tells us that we have a left tail test. That's our claim. Okay, the fourth stage, I kind of embed first and second within step 3 here. So our fourth step is to identify our confidence level is 95%, our alpha is 0.05, and we got that from this phrase right here. We said it was a left-tailed. Again, in t-tests, we are concerned about the sample size is 12, and our degree of freedom is 1 less than the sample size, so our degree of freedom is 11. This puts our critical value at negative 1.796, and I want to show you on the t-table where we got that and how we got that. So when I go to the t-table, and this t-table might look a little different than the one that I had shown you in class, but again, you've got 2 rows at the top. Our first row in this one is the two-tailed probability, the different ones that we test for, and then the second row is the one-tailed probability. Our leftmost column is our degrees of freedom. So we know that we have 11 degrees of freedom, so I'm going to go down to the 11th row and go across, and I'm going to stop here. And I stop there because this is our column for a one-tailed probability where we have 0.05 in that one tail. So our second column in terms of our t-scores. And that would be 1.782. And because this is a left-tailed, that is going to be negative 1.782. If you remember, our t-table puts all of the t-table or t-scores on one chart, and it's up to you to put the positive or the negative depending upon if you're looking at the right tail or the left tail. And we're at the left tail, so we're going to make that negative. Okay, so that's how we got that. So when we go to do our test statistic, we're going to use our formula. Again, this looks so similar to what we were dealing with our central limit theorem. But remember, x bar, we're taking the mean of our sample minus mu, which is what the mean that we're testing, which is, in this case, 7, over the standard deviation divided by the square root of the sample size. So we plug all of this in, and we get a negative test statistic. So it's on the low side, but it's not any lower than our critical value. So that kind of tells us that we're probably not going to reject anything. On the table, this p-value is to the right. I think it's on the right of the table that you have. On my table, it's going to be to the left of the row that we were looking at. So this is not in the significant zone. I don't think I would want to interpret from the table. I would always interpret that from the StatCrunch input. We're looking at our critical value curve. So when I draw the critical value curve, very similar to our normal curve, I put my critical value score in, and I can see that my test statistic is not in the rejection zone. When I do the p-value, to get the exact p-value, I would have to go to StatCrunch. So I probably should just go ahead and do that right now. So I open up StatCrunch. I'm going to go to Stats, down to T-Stats, and I am doing one sample with summary. So I need to put the information in here. My sample statistic is 6.83, and it's really tempting just to leave it at 3, but I would put as many 3s in there as possible. This is a small sample size, and the more digits being accurate is going to give you a better outcome. 1.992409, and I think it was 8.4. Okay, and our sample size was just 12. We are doing a hypothesis test. We're testing to see if the mu is equal to 7, so I need to change that. And then I'm going to do this drop-down menu. We have a left tail test, so I'm going to hit less than, and then I'm going to let StatCrunch do the work. There I have my p-value of 0.387. So that's a pretty high p-value, and if you remember, when the p is high, the null must fly, so this is more proof that we should not reject the null hypothesis. But being I'm in StatCrunch, I'm going to go ahead and show you how to do the confidence interval. So I'm going to hit Edit, and I'm going to go back and click the confidence interval. But this time, I need to identify a confidence interval for 90% because, again, confidence interval is a two-tailed event, and the two-tail, or the confidence level that puts 5% in each tail is a 90% confidence level, would put 5% in each tail. So I need to change this confidence level interval to 0.9, and this is only for the confidence interval. Then I click into my compute, and I come up with a confidence a lower limit of 5.8 and an upper limit of 7.87. So let's go back to this. When I calculated it out by hand using the formula given in our note sheet, we ended up with 5.8 is our lower limit, and our upper limit was 7.9. And when we think about that, I need to slide this down a little bit, this supports the same thing that our previous two methods, because we are testing to see if the null hypothesis is equal to 7. And we can see that 7 is in that interval. We can't possibly reject the null hypothesis, which states that the mu is equal to 7, when 7 actually falls in our confidence interval. So all three of our methods support the decision to fail to reject the null hypothesis. There is not evidence to support the claim that the average hours of sleep for adults is less than 7.